Hello world, it's Craig. This is a solid state music VB1B memory mapped video board, and this is a solid state music VB1C memory mapped video board. In this video, we're going to look at some of the details of how these boards work and point out some important differences between this version C and the previous version B. Now, unfortunately, this version C isn't my board. It's on loan from a buddy, Mark, up the road in Seattle. And he was fortunate enough to collect it last year from the estate of another vintage hardware collector who happened to precede us in death, so we're getting his stuff rather than him getting our stuff. Anyway, Mark sent it down to me last week, and the closer I looked at it, the uglier it got. It was obviously not factory built, and we're guessing it had never actually been operational. I cleaned it up. I soldered a few pins that had been missed on the back. I removed some solder bridges, and there were some long resistor leads that were bent over and shorting. Removed a few other patches and modifications here and there to get it going, and then removed a great deal of flux. And the board really cleaned up nicely, and I've had it running, and it works very, very well. I haven't found any problems with it. Now, going back in time, Solid State Music made the original VB1 Rev 1, which was a very different design than either of these, and then the VB1 Rev 2, which is quite similar in design to these, but I've never actually seen a schematic for either of the VB1A boards. And these two photographs are courtesy of Herb Johnson over at retrotechnology.com. And if I can't find a document online, that's always my next stop, is to get a copy of it from Herb. You probably have been there, but I'll leave a link to Herb's website below. Then the next revision was this VB1B, and that's the same as the reproduction that I made. And then the VB1C, which I believe was the last of the VB1 series. And about the same time as the VB1B, there was the VB2, which is significantly different, and it's entirely port mapped and rather than memory mapped like these two. And then they made the VB3 and the VB3A. In time, we may look at some of these other boards, but right now we're just going to look at the VB1B and the VB1C. You have to study these pretty hard to notice the differences. You know, these look almost identical. Down here by the fingers, some components, they're missing on the C version. On the C version, there is a jumper here that isn't on the B version. And over here on the top, there's a resistor and a diode and a little capacitor that aren't on the B version. So really, those are the only differences between these two, but in terms of performance, it actually makes quite a difference for those little small enhancements that they made between the B and the C. Let's look at these components down here by the fingers that are on the VB1B, but they're missing from the VB1C. Now these are to create the -3 volt and the +12 volt power rails that are required for the Motorola 6570 character generator. The current's so small requirements for that they're really just dropping the voltage from the nearest rail across a resistor, and then they're holding it at the fixed value with some Zener diodes. So that's how they get the +12 and the -3 on the VB1B. But the VB1C used the next generation character generator from Motorola, and this MCM 66700 family has an internal bias generator for the back bias, so it's a single voltage device. And the original character generator listed on the BOM and here in Mark's board is the MCM 66714 character generator. Now you could take the 66700 family generator and put it into the B version, and it works just fine. The family was designed, that character generator, to be backwards compatible with the 6570 family. Most of the versions of this newer one ignore the pins that were previously connected and dedicated to the -3 volts and the +12 volts on the 6570. But you need to be careful, because if you find one of these character generators and you want to use it, some of these versions did repurpose those voltage inputs as additional enables, and I suspect that they really don't like to have that -3 and +12 volts being applied to them. So while this new one is backwards compatible with the old one, the reverse, of course, isn't true. The VB1C has to have that 66700 family, and even though it is backwards compatible with the 6570 family, the 6571 in the VB1B version seems to be much more readily available. where these 66714s can be a little harder to find. And that's one of the reasons why when I made my reproduction, I did it with the B version, and that was because these character generators for the B version are much, much easier to find. Comparing the B version and the C version is much more complicated than it needs to be because there's a large number of mistakes in both of these schematics. So even though the changes were minor between the B and the C, they did a complete schematic layout change, and they reduced the schematics from 6 pages in the version B down to only 2 pages in the version C. So in the end, while the schematics are much easier to follow for the version C, or for every mistake they fixed, it seems like they made at least one more mistake. Now, getting rid of the -3 and the 12 volts that are required on the B and aren't on the C, that was an important step because chips like the 8080 and the 2708 that required these voltages had become obsolete by the time this C came out. And nobody wanted to be the one to build the last board that needed these two power rails, particularly the -5 volts or the -3 volts. Since the character generator was the only thing needing that +12 and -3 on the B version, the C version no longer needed those supplies at all, and so that's why all of these components down here in the bottom are missing on the C version. Now the next change is very minor when looking at it on the schematic, but it eliminates that sparkling snow that I mentioned in my last video. While they called it sparkling in the user's manual, in reality it's more like meteors streaking across the screen. So I'm going to deep dive now into how the memory access works on these two boards, and it's the same for both boards. So I think it's time well spent, but be forewarned. So let's compare U13 in the version B on the left to the same portion of the circuit for version C on the right. And you can see that the set input to this latch is tied to a soft 5 volts in version B, which makes it permanently disabled. In the version C, there's a 2-position jumper that allows the latch preset to be taken to that same soft 5 volts, just like it was in version B, or it can be connected to this select signal that also goes down to the clear on the 74166 down here. And that is this jumper that we looked at earlier here by U14. Now this 74166 is the character generator output shift register. So whatever character or graphics block is being sent to the terminal, one scan line of it is loaded into this parallel in serial out shift register, and then it's shifted out to the video drivers to form that one line of that one character or graphic block. Then the memory pointer on the board is advanced to the next location. That data is received from memory and loaded into the shift register, and then it's shifted out, and then the process repeats. So now going from version B to version C, this is actually a 2-part change. There's also this diode and RC pair. Well, we'll get to that in a little bit later, and this is the diode and resistor added up here in the top right corner. But for now, it's enough to know that this signal coming through this diode is the same active low board select signal that it is in the version B. So let's pretend that this diode and RC isn't even here for the moment. Now this jumper is the important change to deal with that snow, and for such a tiny change, it has an enormous impact on the video quality. Now obviously, if the jumper is put to the right, then this latch operates the same as the version B. So when it's to the left is the new part. That's the interesting story. This board has 1K of RAM that can be accessed either by the video output circuit or by the CPU. The video output has a bank of counters here on page 2 that's just sequencing through the entire memory, one character at a time. And meanwhile, the CPU is doing normally memory cycles. And those memory cycles, sometimes involve this card to read and write those characters or graphic blocks that need to be displayed. So these are completely asynchronous. The video output is running by this 12.44 megahertz crystal, while the CPU read or writes memory whenever it needs to. But the CPU has to have priority. Anytime this board is addressed by the CPU, when P-sync and Phi1 are both high, and the bus address matches the address of this board as determined by this DEM8131 comparator against the dip switch, and it is not a port cycle, then this select signal is asserted. Now that select signal changes who has control of the video RAM. Normally, the video card controls the address through those bottom drivers, and the RAM address signals RA0 through RA9 that are sequenced by the counters that we saw back on page 2. But when this select is asserted during a CPU memory cycle, either read or write, those drivers turn off, and these drivers up here are enabled, so the 10 lower addresses from the bus now controls the RAM. You can see here at the bottom that the bus data just directly connects all the time to the data input of the RAM. Now going back to this board select signal, in version B, that signal does all the work. But in version C, that signal is double buffered by this exclusive OR and this inverter to create X select. But when all is said and done, the signal logic of X select is the same as select because it's double inverted. It's just additionally buffered because they need it to hit a hard logic low, because here on page 2, X select comes into the cathode of this little germanium signal diode. When X select goes low, it pulls this abbreviated select signal low through that diode. That select signal on the anode of the diode follows that down whenever that signal goes low. And this part of the signal goes to the shift register and also up to that jumper that we looked at earlier. If we took out this diode and this little RC and tied that jumper to the +5, then it's exactly the same as the B version. So the video counters are continuously sequencing through the memory to output the characters one at a time, but at some point the CPU needs to read or write characters to that same memory block. But since the video memory is not actually dual-ported memory like we think of today, it cannot be accessed by the CPU and the video output at the same time. So whenever this board is being selected for the memory cycle, the video read is blocked, and the video output simply skips over whatever character it was on, and the CPU is given access to the memory. And that's the blanking that they talk about in the user's manual for these. And both of these boards have that amount of blanking. And that blanking itself is very simple. Down here on U8, the board select signal clears the contents of the shift registers so that it outputs a string of zeros rather than the actual character or graphic bits. And the entire time the CPU has this board addressed, in either version, these zeros go out to the screen whenever the CPU is accessing the memory, and so that video during that time period is just blank because this shift register is just shooting blanks, putting out zeros. But the question is, if the shift register is just outputting zeros, then what causes the snow, and how does that jumper in the version C eliminate that snow? So let's go back to page 1 of the schematics. Now, data from the video RAM comes out of the RAM through these drivers, and with these drivers up here, they can go onto the bus during a memory read. But right now, we're interested in these 8-character byte signals, DIX, that tap off and go to page 2. Now here on page 2, those data lines come into the graphics pattern generators here on U5 and U15, and also to the character generator U16. So at any one time, this board is making and forming whatever the graphics pattern is, if that's going to be interpreted as a graphics pattern, but it's also generating the character if it's going to be selected as a character. And then both of those signals go to this pair of multiplexers, U6 and U7, and that's when it gets selected between these two generators, either graphics or character. Now, if it's in character mode, the output from the character generator feeds the shift register, and if it's in graphics mode, the output from the graphic generator is going to be fed into the shift register. But notice that only the lower 7 data bits are used to feed the graphics and character generators. The most significant bit up here is DIX7, does not go into the character generator or the graphics generator or the shift register. That 8th bit is the mode control bit. Now it comes out of the video memory along with the other 7. So when you're writing to this board, if you want the character or graphics, that 8th bit is written at the same time and it's stored in the RAM, but it directly controls the mode of the character. So this bit, along with the graphics switch that is here on the board, creates 4 operational modes. Now that 8th bit gets inverted by the exclusive OR with the 1 input tied to the soft 5. It's then the D input, so it's latched into U13, and also it comes down here into U18, which is actually an OR gate. It's not a NAND gate. That's a mistake in the schematic. So this is actually an OR gate. So let's look at it where it goes down to U18 first and then come back to the latch later. If the dip switch is in graphics mode, so it's closed, then this input is low and this OR gate is, let's say it's enabled, because whatever that 8th bit happens to be, it then comes out and controls the output of U18. And that signal comes back up to the select input of these two multiplexers, U6 and U7. So the most significant bit comes out of memory. It's inverted by U4. Now, if U18 pin 12 is low, then the output of U18 OR gate is the same signal, meaning it's still inverted. That goes into the select of the 74157, which when low selects the A input, and when high it selects the B input. A is the graphics generator and B is the character generator. So in graphics mode, the select is the opposite of the memory value. So if you put a 0 in that most significant memory bit, this S input is 1, so the character generator at input B is selected. Make the most significant bit a 1, this select input is 0, so the graphics generator at input A is selected, and the graphics character is what is sent to the shift register U8. So that's how the 8th bit directly selects between graphics generator or the character generator. When writing the character to memory and the switch is in graphics mode, the most significant bit determines if the other 7 bits will be interpreted as a character or as a graphics block. Okay, so that was in graphics mode. Now, if that switch is open, meaning the board is in only character mode, then U18 pin 12 is high and U18 is disabled, meaning that the output of U18, which is, again, actually an OR gate, is set at logic 1. So the multiplexer input now is always 1. So this multiplexers are always sourcing from the character generator. So it's only in character mode. So now let's back up to where the 8th bit was latched. So that D input was inverted for memory bit, so this Q bar will be the same logic as it was stored in memory. Q bar comes down to this AND, which is now enabled because the switch is in character mode. U2 pin 1 is high, so the output of U2 follows the input on pin 2. And that logic will be the same as the most significant bit as memory. So when that memory bit is low, when the output of U2 is low and this exclusive OR just passes through the signal on pin 4. And that signal is the output to the shift register. It's the output from the shift register, which is the video bit stream. And that stream goes up to those video drivers that we looked at before here at the top. Okay, so that's with the bit low and it's in standard character mode. If that 8th bit is high, the output of U2 is high and this exclusive OR is now operating as an inverter. So it's now opposite day. Black pixels become light pixels become black, so the output stream is now in inverse video. And therein lies the problem. That 8th bit is somewhat of a loose cannon because even if the shift register is cleared and only sending out zeros to the display driver, that 8th bit still controls normal or inverse video mode. Now, this isn't a problem when it's in graphics mode because that just swaps between the two inputs of the data selectors, U6 and U7, but no matter what they're feeding the shift register is sending out zeros because there is no inverse mode in graphics. So all those zeros go all the way to the video drivers. But in character mode, that 8th bit can flip this U4 between normal and invert mode, and that changes the output of that pixel. And that's what causes the flashing or the snow when we get random toggling of that 8th bit when we're in character mode. So let's look at a little video of the snow on the VB1B without the improved circuit in what I would say is kind of a throttled memory update. Now, this is not the worst case because the CPU is not accessing memory as quickly as it can. There's a delay counter of 100 between outputting the characters. Notice that the snow only shows up when the character being written is in inverse video, and the rest of the character screen is in normal video. So that 8th bit is being set to 1 and turning that stream of zeros from the shift register into lit pixels. And in this little demo program, the character itself is just being incremented, and then that character is being written into the next memory byte. So once we get to the inverse video mode, where the characters have that most significant bit set to 1, then each character causes the streak. Now, it isn't so bad in normal use where you've only got 1 or 2 characters around that are in inverse video, or maybe you just have the cursor in inverse video. So if you just have a few things in inverse video, then this doesn't show up. And if none of the characters were in inverse video, then there wouldn't be this 8th bit problem at all. Now remember, the memory location being addressed by the CPU and the memory being read to create the display line have nothing to do with each other. When we see the glitch on the display, that glitch or that streak shows up just where the video happened to be outputting the signal when the CPU memory cycle occurred. So it doesn't matter which memory location was being written to, it just matters where the scan happened to be on the screen, and that's where that little streak is going to show up. So that's how the snow is created, and that's exactly the same on both boards. And it's created when that 8th bit is messed up. What is fiddling with that 8th bit to cause the problem? And that goes all the way back to the 2102 RAM and exactly what's happening during a memory cycle from the CPU. When this card is addressed, the memory cell address comes from the CPU. If it is a write, the CPU is putting data onto the bus here into the RAM. If it's a read, then the RAM is putting its data onto the output pin that goes through both of these buffer banks and onto the data bus back to the CPU. So during a memory read, whatever data is in the memory location that's going to the bus, to the CPU, that 8th bit is still controlling the inverse video mode. So if that character being read happens to be a graphics block or an inverse video character, then its most significant bit will be 1. And if the board is in character mode, that 0 output stream from the shift register turns into lit pixels and we get a streak across the screen wherever the raster is. So that's during a memory read, and one would think that that's the end of the problem because that's when we're getting a byte out of memory that we have no control over, but it's not the end of the problem. It gets worse. And that's because during a memory write by the CPU, the 2102 RAM becomes transparent, meaning that the data presented at the data input pin from the CPU is being pushed to the data output pin. So that 8th bit is still controlling the inverse video even during memory writes. Here's a video with the delay counter set to a much smaller value than it was in the last video, and the board's configured as a V1B without the improved 8th bit override circuit. You can see that the screen is just full of these lines where the inverse video bit is true. Now, in this photograph, the CPU is updating the video memory, but the video scan happens to be up here. The memory write had the most significant bit set, so this line of video has the pixels illuminated during that memory write. The shift register was sending out pixel off, but it was opposite day, and the invert mode was then turning them on, creating this line. But this line only lasts for the duration of a write cycle. By the time the next memory cycle comes along, the video raster is somewhere else on the screen, and so the line is put down there. So to be clear, these random lines only show up when the video memory is being read or written from the CPU side. If the screen isn't being changed, then there is no snow. Now in version C, solid-state music didn't actually eliminate the problem, they just made it less noticeable by forcing the video bit to 0 to make sure those lines just don't show up in inverse video, meaning that they'll be blank lines rather than lit lines. So let's pull it together and see how that latch how this all works. If E2 and E3 are jumpered, so now that select line, the same line that takes U8, the shift register, and forces it to output zeros, that same line forces the output of that latch to 1 because pin 10 is the set enable. So that forces Q to 1, so Q bar goes to 0, and Q bar, of course, is that 8th bit. That comes down here to put us into either normal or inverse video. And so that forces it into normal mode. So whenever the circuit has U8, so it's outputting zeros, at the same time, that latch is held, so it has to output a 0 and keeps us into normal mode. When we're done reading this board with the CPU or writing to it, then that RC pulls the select line up. U8, that 74166 shift register, starts outputting normal characters, and about the same time, that preset is released on that latch, and so now that latch goes back to outputting the actual value of that bit 8 rather than holding that value low, and so we're back into the normal operation of this video output. Here is another video with the glitch filter enabled. And you can see that even when it's writing the inverse characters, there aren't the streaks across the screen that we saw before. For such a simple solution, it's very effective. And that's because a randomly lit pixel on the screen is easily noticed, and it's there until the phosphor dies out. But a randomly off pixel is hardly noticeable because it was most likely refreshed in the last scan, or maybe it'll be refreshed in the next scan. And we have that extra time, of course, because of the persistence of the phosphor on the screen. Now, in this photo, you can see that the dim lines are not that offensive. Using the monitor and you really concentrate, you'll notice these faded streaks, but they're not nearly as noticeable as the bright streaks were. Okay, so that is the big difference, other than the character generator family. That's the big difference in the performance of these two boards, and it gives the version C a nice edge over the version B if you happen to be using a lot of inverse video. Okay, finally, let's get back to that diode and RC pair that's on that select signal. And so this is the final difference between the version B and the version C that I found. As we just went through, when the board is selected and that X select line goes low, this diode drains the capacitor and pulls the select line low and clears the shift register. When the memory cycle is over and the cathode of the diode goes high, so it's not selected anymore, so this goes up high, then the blanking signal floats high according to this RC time constant. So it doesn't go high right away. It's got to be pulled high by this resistor, and as that resistor charges up this capacitor. So let's look at these on the logic analyzer. What we have here, the top trace is the board select line. So that's when the CPU is doing a memory read or write. The next one down and the analog trace at the bottom are the output of that RC, which is also the shift register blanking signal. You can see that the board select is released after the CPU memory cycle, and then this RC starts charging up, and there's a bit of telegraphing, and then the shift register is back into normal operation. Okay, the third trace down, the quick square wave, is the bit clock. With each cycle of that clock, the shift register is putting out 1 bit to the video, and that becomes a pixel. The next trace down is the shift register reload. So when all the bits have been sent out to form that one line of that one character, this loads the one line of the next character, this to be serialized and go out to the video drivers. So there's one more trace, and that's the actual data that happens to be coming out the shift register when this captured was taken. With the telegraph noise and the indeterminate state, it's hard to tell exactly how long the blanking period takes when this gets back to normal. I think the easiest way to do it is just let's compare these from looking on the videos I took and do a couple of screen grabs. So this is the VB1B without the correction. We can see we're getting streaks, and if we stop it, we can see that the streak is about 4 characters wide. In fact, here with the 8s, we can see this is almost exactly 4 characters. So that's how long just the bare CPU memory cycle took. It took about 4 characters, because here, as soon as that cycle was over, since it didn't have that RC pair, it immediately starts shifting out the video again. Now let's compare that to with the correction, and we can see it's not that bad. Here, instead of the bright streaks, we're looking for the dimmer lines, but it's really only maybe 6 characters, maybe 7 characters. So at most, it looks like we're throwing away, 3 or 4 extra characters. Now they could have timed this much better using a one-shot, or they could have used a Schmidt trigger to get rid of some of that telegraphy noise. But all in all, considering they did this with without adding any extra ICs to the board, it's a pretty good job. It's very effective. So rather than adding another IC, we can throw away those 3 or extra characters or so that are affected by the blanking period. Okay, that's enough about these boards for this video. Now, the reason I even brought this all up is because I'm making a list of revisions I want to make to my B version. This is the one I talked about in the last video. And I wanted to see how well that 8-bit forcing 0 scheme in this C version worked. So this is my reproduction B version, and I just have a little mod here. I have pin 10 of that latch lifted out of the socket. That's the set input, and I'm bringing a blanking signal over, and I basically just mocked up the function of that jumper on my B version, and it seems to be as effective at snow removal as it was in the version C, so I don't really see a reason to leave that off the next revision on the board. It would just be a matter of pride to have this completely or closer to the original, but that is a nice enhancement to get rid of that snow. So I think it's worth adding those improvements to my B version, making a B plus version, I suppose. It's still going to use the 6570 character generator, but with the improved blanking. Now another change, and one that I pointed out in the last video, is there's a little patch required. There's a trace cut and a little patch added to the back of this that was required to extend the back porch on the vertical sync signal. And I didn't just pull that patch out of thin air. After I noticed the problem, I started looking at the schematic for the C version, and I noticed they had corrected the back porch problem. So that's going to be another correction that I'll do to the next version of this. And I've since come to believe that the mistake in the B version was not an engineering error. It was simply a drafting error, because I've asked a number of people who have B versions, original solid-state music boards, and I had them check their board and see how it was fabricated. And at least on the 6 or so boards that we've talked about, the version B boards, none of those were built to the version B schematic. So I think that was just a drafting mistake and not actually what was put onto the board. I'm guessing that the draftsman simply put the wrong signal on this U4 pin 9 rather than not vertical blank. This should have been not vert 1. Now, there's one more thing I'm toying with. I have no idea why Solid State Music thought these 0.156 Molexes on the video board was a good idea. And so I think in this space, I will put another footprint for a standard RCA type connector. And so, that'll just have the 2 footprints there. You can mount either of these 2 connectors if you want authenticity or if you want convenience. Some other boards at the time were using these RCA connectors, so it seems like rather an odd choice to use these Molexes. Okay, well, that is it for this video. If you're one of the people that are building one of these VB1Bs, this first version, let me know if there's any other changes that you have come across that you would like to see in this, because I think I am going to go ahead and make these changes pretty soon. Next time I need some other boards, I'll submit the job to have these made. All right, that's it for this video. Thanks for watching. I will talk with you later. Bye-bye.